Hello, my name is Gautam Prakriya, and I'm going to be talking about direct sum and partitionability testing over general groups. This is joint work with Andrei Bogdanov. This paper is concerned with property testing of functions. The setting here is we're given a function, and we want to determine whether the function satisfies a certain property or is far from satisfying this property. And we'd like to do this without looking at the entire function table. That is, we want to query the function at a small number of points to distinguish between these two cases with high confidence. The property that we're going to be interested in is that of being a direct sum. A direct sum is a function from a product domain to an abelian group that can be written as the sum of univariate functions on the coordinates of the domain. Of particular interest to us is going to be the setting where the domain is the Boolean hypercube. In this setting, f is a direct sum if and only if f of x can be written as g0 plus g1 x1 all the way till gn xn, where g0, g1, etc. are elements of the abelian group, and g dot x is just the group element g if x is 1, and is the identity element 0 if x is 0. Note that this tells us the direct sum generalizes affinity. In particular, if, say, f is a function from the Boolean hypercube to the field of two elements, then f is a direct sum if and only if it is affine. Direct sum testing was previously studied by Dinur and Golubev, who gave a 4-query direct sum test for functions with range f2, the field of two elements. The crux of the test is a reduction from arbitrary product domains to the Boolean hypercube. Now, since functions with domain, the Boolean hypercube and range f2 are direct sums if and only if they're affine, we can simply use the affinity test of Blum, Luby, and Rubenfeld to determine if the original function was a direct sum. In this talk, I'm going to focus on our main result, which is a 4-query test for direct sums from the product domain to arbitrary abelian groups. Turns out that the reduction from arbitrary product domains to the Boolean hypercube carries through in our setting as well. And this reduction builds on ideas of Dinur and Golubev. Our main contribution is a direct sum test for functions from the Boolean hypercube to arbitrary abelian groups. Okay, and I should point out here that the test of Dinur and Golubev is designed specifically for the case where the range is f2, and their test doesn't really make sense when the range is an arbitrary abelian group. Okay, so let's look at our direct sum test. So we're going to begin with a simple observation. Note that if a function f is a direct sum, then f of x plus f of y, where x and y are 2 points in the domain, must be equal to f of xsy plus f of ysx. So xsy is the string that matches x on indices in S and matches y on the remaining indices. And ysx is the string that matches y on the indices in S and x on the remaining indices. So it should be clear that if f is a direct sum, then this equality holds. And it turns out that the other direction holds as well. And this is a simple exercise to check. So given this observation, a natural attempt at a direct sum test is the following. Okay, we sample x, y, points x, y from the Boolean hypercube and a partition and a subset S of the set of indices uniformly at random. And then we simply test if this equality holds, right? So if f of x minus f of x as y minus f of y as x plus f of y is equal to 0. If it does, we accept. Otherwise, we reject. For the rest of this talk, I'm going to use the shorthand dfs semicolon x comma y for this expression over here. Okay, so let's look at what guarantees we can show for a direct sum test. Let's start with some notation. Let rho of f denote the probability that the function f is rejected by the test, and delta of f denote the distance between f and the set of direct sums. So we measure distance as relative. By distance, I mean relative Hamming distance. So the guarantees we have for the direct sum test are the following. The test accepts with probability 1 if and only if f is a direct sum. Note that this is essentially the observation that we saw on the previous slide and is easy to verify. In the other direction, we show that there exists a universal constant C such that the distance between f and the set of direct sums is bounded by C times the rejection probability of the test. Okay, so this is the soundness guarantee of our test and is going to be the focus of the rest of the talk. And I should mention here that the constant C does not depend on n, okay, the domain size. So it's a universal constant. Okay, so for the rest of the talk, we're going to focus on analyzing the soundness of this test. But before jumping into the full soundness analysis, let's consider a simpler setting. Let's suppose that we're given a function f that is a direct sum that has been corrupted on some small fraction of inputs, say a delta fraction of inputs. So in this picture, the corrupted inputs lie in the shaded region, and we'll call this set B. Now, note that the test is going to reject if exactly one of the 4 queried points x, xsy, y, and ysx lands in the shaded region. So let's try and compute the probability that x lands in the shaded region and none of the other points land in the shaded region. So this is going to be a low bound on the rejection probability of the test. Okay, so in order to compute this probability, we need to compute probabilities of the following form. What is the probability that, say, one of the other 3 points lands in B conditioned on x being in B? Okay, so this is easy to determine for y since x and y are independent, and this probability is just delta for y. But what about the other 2 points? X as y and y as x are correlated with x. Okay, so the key observation that allows us to bound these probabilities for each of these points is the following. We can view x as y, the same holds for y as x, as the result of passing the string x through a binary symmetric channel. Okay, so what I mean by this is the way the channel operates on x is the following. Each bit of x is flipped with probability 1/4 and left unchanged with probability 3/4. Okay. So this observation allows us to use a property property of the binary symmetric channel called small set expansion, okay, which allows us to get a bound on the probability that XSY lands in B, given that X is in B. Okay, so the bound we get is delta to the 1/3. Now, putting everything together, note that this bound also holds for Y as X, so because of symmetry. So putting everything together, we get that the rejection probability of F, the probability that the test rejects F, is at least delta, which is the probability that X lands in B, minus delta square, which is the probability that both X and Y land in B, minus 2 times delta to the 4/3. So this sounds great, but unfortunately, if delta is large, the right-hand side of this inequality is going to be negative. So it doesn't really tell us anything about the rejection probability. Now let's look at our full soundness analysis. The high-level structure of our argument is very similar to that of the BLR linearity test. The idea is to view direct sums as a code, as a linear code, and to view this function f as a code word that has been corrupted on some fraction of bits. And what we'd like to show is that f has been corrupted on a fraction of bits that's at most a constant times the rejection probability of f. Okay, so in order to do so, we're going to use a decoding rule that hopefully decodes f and then argue about the number of changes that were made to f. And the decoding rule that we use is the following. So we define this new function phi of x as the plurality, that is the most common value over all choices of y and s of f of x as y plus f of y as x minus f of y. And what we'd like is for phi to be order rho of f close to f. And this is easy to show using Markov's inequality. And in an ideal world, we'd like phi to be a direct sum. Unfortunately, this might not hold. For example, consider, let's suppose f is a direct sum that has been corrupted on points of relative Hamming weight at most 1/3. So then phi of 0, let's consider phi of 0. So phi of 0 is going to be the plurality of f of 0s y plus f of y as 0 minus f of y, or all choices of y and s. But x 0s y and y as 0 are typically going to have relative Hamming weight around 1/4. And so the function value f is going to be corrupted on these 2 points, which means it's unlikely that phi of 0 is going to match a direct sum. So in order to get around this, we need to relax what we require of the function phi. So instead of asking for phi to be a direct sum, we're going to ask for something weaker. We're just going to require that the probability that phi is rejected by our test is half of the probability that f is rejected by the test. Okay, so this is our progress measure. So then, in order to show that f is order rho of f close to a direct sum, we simply apply this decoding rule iteratively. And so what we get is that delta f, the distance between f and the set of direct sums, is at most 2 rho f, which is the distance between f and phi, plus 2 rho f by 2, which is the distance between phi and the function we obtained by applying the plurality rule to phi, plus 2 rho f by 4, and so on. And so the distance between f and the set of direct sums is at most 4 times the rejection probability of f. We're now going to prove that the rejection probability of phi is upper bounded by half the rejection probability of f. The proof of this statement uses a combination of algebraic and analytic tools. The key lemma in the proof of this statement is the following. It states that for all but a little o rho of f fraction of x, that is for most choices of x, the plurality that defines phi of x is in fact a strict majority. So jumping ahead a bit, let's look at why this lemma is relevant. So we want to analyze the rejection probability of the test on phi. Okay, so this is the probability that this expression is non-zero. And we want to relate this quantity to the rejection probability of f. In order to do so, we make a series of substitutions to the terms in this expression. The key lemma allows us to argue that the value of this expression remains unchanged after these substitutions are made. So now let's look at the proof of the key lemma. So we're going to start by a well-known fact that says that the fraction of votes that make up the plurality is at least the collision probability. The collision probability is the probability that two randomly chosen votes are equal to each other. That is, let's pick y, s uniformly at random and z, t uniformly at random. Then what's the probability that their contribution to this plurality is the same? So it suffices to show that for most choices of x, the collision probability is large. And this is what we're going to focus on now. So in order to prove that the collision probability is large for most choices of x, we're going to use the following algebraic identity. The algebraic identity allows us to relate the collision probability to the rejection probability of the test on f, on correlated inputs. Okay, so these are not necessarily random inputs. So in order to prove that for most choices of x, the collision probability is large, it's sufficient to show that for most choices of x, the probability that the right-hand side of this identity is zero is large, or the probability that it's non-zero is small. So for this talk, we're just going to focus on a single term on the right-hand side. And we're going to prove that for most choices of x, the probability that that term is non-zero is small. But first, we're going to take a short detour, and I'm going to introduce the binary erasure channel. The binary erasure channel takes as input a bit and outputs either a bit or an erasure. The binary erasure channel with erasure probability E takes a bit x as input, and with probability E, it outputs an erasure, and with probability 1 minus E, it leaves the bit unchanged. Coming back to the proof of the key lemma, we want to prove that for most choices of x, the probability that dfs xsz y is non-zero is small. Recall that dfs xsz is shorthand for f of x is z minus f of x is y minus f of y is z plus f of y. The key insight that allows us to bound the probability that this expression is non-zero is the following. We can view the queried points x is z, x is y is z, and y as the result of passing x through a binary erasure channel. Note that if a coordinate of x lies in S, then the corresponding coordinates of these queried strings are x, x, y, y. Okay, so there's no erasure because x is still present in the output. We know everything about x in the output. On the other hand, if a coordinate of x does not lie in S, then the corresponding coordinates of these queried strings are z, y, z, y. So these are just random bits. Okay. So this corresponds to an erasure. Now, what this observation allows us to do is it allows us to use a property of the binary erasure channel called hypercontractivity. And in fact, this bound in this claim follows immediately from the hypercontractivity of the binary erasure channel. So this completes the proof of the key lemma. Now that we have the key lemma in hand, let's return to the proof of this statement, which says that the rejection probability of phi is at most half the rejection probability of f. So recall that in order to relate the rejection probability of phi to the rejection probability of f, we make a series of substitutions. And these substitutions have some randomness associated with them that comes from the strings z and w and the set t. So these things are chosen uniformly at random. Now we can use the key lemma to argue that for all but a small fraction of choices of x, y, and s, a little o rho of f fraction of choices of x, y, and s, the substitutions do not change the value of phi of x minus phi of xsy minus phi of ysx plus phi of y with high probability over the choice of z, w, and t. All right, so with this in hand, let's look at the expression post-substitution. So we use another algebraic identity to rewrite the expression post-substitution as a linear combination of the test run on correlated inputs. Okay, so now what we are interested in is arguing that this expression is 0 with high probability for most choices of x, y, and s. Okay. So in order to do so, we use the hypercontractivity of the binary erasure channel again. And we use it to show that for all but a little rho of f fraction of x, y, and s, this expression is 0 with high probability over z, w, and t. So I'm not going to present the details of this argument due to time constraints, but it's not very different from the argument we saw earlier. So now we have these two statements. One, that these substitutions for most choices of x, y, and s, these substitutions do not change the value of the original expression with high probability. And two, that for most choices of x, y, and s, the expression post-substitution is 0 with high probability over z, w, and t. And so using a union bound, we can conclude that for all but a little o rho of f fraction of x, y, and s, there exists a fixed strings z, w, and t such that 1, the substitutions do not change the value of the original expression, and 2, the expression post-substitution evaluates to 0. Okay, so what these two statements together tell us is that for all but a little o rho of f fraction of x, y, and s, the original expression phi of x minus phi of xsy minus phi of ysx plus phi of x is 0 always, right? And so this tells us that the rejection probability of phi is in fact little o rho of f, which implies that the rejection probability of phi is at most the rejection probability of f by 2. Okay, so this completes the proof of soundness of our test. I want to end this presentation by mentioning that in our paper, we study the question of testing certain other function properties. These are called partitionability properties, and they ask whether a function can be decomposed into lower dimensional functions on disjoint sets of inputs. Thank you for listening.